Let's go ahead and get started. Hi, everybody. If you're just coming in now, turn your homework in, and that's it, yeah. I don't know what else to tell you. I suppose now's the time that I should say thank you for coming on time and turning in your homework appropriately. You guys are the real heroes, right? I think that's the point here. I'll take that, sure. Thanks. Okay, so today we've got ISE 102. That's cool. We're going to do more uniform series stuff. That's going to be neat. And then it's going to be the weekend, right? So, looking sharp. So first, brain teaser. A glass cup contains oil and water. I don't know why it has to be glass, but it contains oil and water. And we add more water. What's it going to look like? Is it going to look like A, B, or C? Yeah, I'd say so. It depends on instantaneously or afterwards, right? But after it settles, the oil is going to sit higher on the top. And it's actually kind of neat that you can actually measure the thickness of a drop of oil by looking at how it expands over a pond. That's really off topic, but it's an interesting thing to do, I suppose. So let's start talking about ISE 102. What are we going to start class with today? What do we usually start class with? Yeah, the most important things you learned last class. So what are the most important things you learned last class? When you come into class, step 1, take your headphones out of your ear. Step 2, put your celly-telly away. Step 3, gloss your lips. Step 4, get out your pen and paper and start reviewing your notes from last class. You can turn that in later. Sue. Good, yeah, really understanding in depth what it is that we're learning about. What else? Most important concepts from last class. Yeah. We did talk about time value of money. That's still pretty important. Good. Richard. Opportunity cost, yep. What about chapter 4 and repeating series of payments? Right, that's like the core of what we're learning right now. We learned one piece of money at one period of time to some future time, or some future time to one present time. Now we're doing a bunch of repeating costs. That's the whole point of this chapter. I think that's pretty important. Understanding how those work at a fundamental level is going to be an important concept. Why don't you get ready for some more learning. Okay, so last class I think we went up to example 4.5. We were talking about somebody who was offering to pay you $6,800. You were going to pay them for $140 a month for 50 months, and we found out that that is a good or a bad deal. Right, we were looking at this problem, $140 a month, but you pay $6,800 early. Eric, you can wait till the end of class. And so we looked at that being a bad deal, right? Because we're going to reject it because the present worth of that uniform series is not the same as what they're trying to sell it for us. So then we started looking at how you can calculate what that rate of return is going to be. And we looked at using the compound interest tables that are in the back of the back of the textbook that give us interest tables for every different interest rate and different number of years, different number of periods. And so we can find out what that multiplier is for different interest rates such as 0.5%, 0.75%, et cetera. And those are all in the back of the book. Right, all of these interest rates. If you are looking for the compound interest factors and you think, man, I don't have the book, then you can find them on Canvas in a couple of places. The first place you can find them on Canvas is that they're uploaded to the Canvas under the book resources. The other place that you can find them is that we just started a discussion about a cheat sheet for your midterm. And in the cheat sheet for the midterm discussion, I posted links to past cheat sheets that students have used in this class, as well as a series of compressed compound interest formulas that might be useful for you guys on your cheat sheet. So going back to that cheat sheet topic, this is up to you guys. I'm happy to let you guys have a cheat sheet for the midterm. If you, as a class, don't work together to generate a cheat sheet that you all approve of, then you're going to get this cheat sheet and nothing else. And that's fine with me. Like, I absolutely think this contains everything you need to know. But if you want to supercharge it or make it cooler or draw pictures of birds or the Spartan logo or anything else you want to put on here that might be helpful, some example problems or anything else, definitions, anything that you think would be helpful for the test, these are all things that I've seen on past student cheat sheets, then absolutely, by all means, work together as a class to come up with a revised version, and then you guys can use that for the midterm. So at the beginning of class on Tuesday, I expect one person to give me a document that I can use both sides for the midterm exam that you all work together on. There's a discussion topic on Canvas. If you guys don't want to do that, we'll just go with this. That's fine with me too. Questions about that? Who is interested in working on that? Why don't you guys raise your hands? Raise your hands super tall so you can look around and see. So there's a couple of people raising their hands. Raise your hands really tall. Okay, so look around at the other people raising their hands, catch each other's eyes, and then make sure you guys come up to the front of class at the end of class and discuss what you want to do. If you have any other input, go talk to them. Snapchat them what you want on the... don't do that, because I don't think you can... Then you wouldn't be able to save the photo, so that wouldn't work. Instagram it, I don't know, Facebook it, whatever. You guys get the point. Questions about the midterm, because we're about a week away. Well, all right then. So let's move on. And when we've talked about these problems so far, we've talked about having a uniform series. We've talked about having one dollar amount at one period of time and then transferring that to another period of time. But you can combine those concepts. And that's what this problem's trying to do, is it's saying we've got this cash flow where at year 1, year 2, and year 3, I have $100 income each year, but I don't pay it back right away at year 4. I don't pay it back at year 3 or at year 1 like we've been learning for uniform series. I'm going to pay it back at year 5. And that's a little bit different than what we've done so far for uniform series. And the difference is that we really have this gap. With a traditional uniform series, if we were looking at an F value with a uniform series, you'd have the F value here, right? Because it'd be right at that last period. If you don't think that's the case, take a look at your cheat sheet that you've got so far and look at the sinking fund or the series compound amount uniform series. And you'll see that the photo shows that there's nothing at year 0, and then you've got arrows that go up until the very last payment, then you have an arrow that goes down, or vice versa. And so if we were solving for F using the uniform series equation only, then we would end up solving for the F period here. If we were solving for P, we'd end up solving for right here. So how can we solve for an F that's at a different period of time? What can we do? Yeah, in the Mars shirt. Say that one more time. Absolutely. Find P or find F given P. And so we can then We understand how to calculate this uniform series either to find a p-value or to find an f-value. Doesn't really matter. We know how to do either one. And then we can convert either from year 3 from year 3 to year 5 or from year 0 to year 5. We can do either one because what we're doing with year 0 to year 5 or year 3 to year 5 is exactly what we learned in chapter 3. It's just transferring a lump sum of money from one period of time to a lump sum of money at another period of time. So you could think about this a few different ways. One of these ways is if you never learned chapter 4. We'd gotten up to chapter 3, you thought this is the coolest topic ever, and then global destruction. And you never got a chance, although you were on the edge of your seat, to learn chapter 4. You'd still be able to solve this problem. It would take you longer, but you'd solve this problem by assuming that you have 3 payments. This would be a p-value, this would be a p-value, and this would be a p-value. And if you add each of these f values together, this one plus this one and this one, those 3 combined would be the same as the answer. To do that, you need to do 3 equations. You have to find f1, f2, and f3, and so you have find f given p at 4 years, at 3 years, and at 2 years. And so what we're saying is 1, 2, 1, 2, 3, and 1, 2, 3, 4. That's where you get those. And so it doesn't base it on when 0 is. That's where you get those numbers. And we solve the problem and we find out that the interest, the payment, the worth at the end of that 5th year would be $459.24. That would be one way to do this. If the world ended after chapter 3 and you were sitting there post-apocalyptically and you thought, I loaned this guy $100 for 3 years before the world ended and now he owes me money. How much does he owe me? And I've got nothing but pen and paper to do it with. This is how you could do it. Don't do that if the world ends. Spend your time doing other things. But this is how you'd solve that problem. If you never learned chapter 4, but we did learn chapter 4. And so, because we learned chapter 4, the first thing that we can do is we can assume that we can calculate a uniform series, that we can convert this uniform series of $100 to one f at a later date to find this f at year 3. Do you guys feel comfortable being able to do that after the last few classes? Yes? Does anybody want me to go over how to do that? Okay. And then, what we want to do is we want to convert f at year 3 to f at year 5. And if you look away from the screen for just 1 second, I'm going to do a magic trick. So just look over there. Ha-ha! It's now p at year 3 to f at year 5. Ta-da! Right? And so really all this is what we learned in chapter 3, find f given p. Okay, really mediocre magic trick, right? I get it. That's why I chose teaching instead of something else. But the reason that this is useful is because then I have 2 equations. I have this equation and I have this equation. And that's it. I don't have 3 equations I need to solve. I have 2 equations. And that's if I only have 3 parts. If I go back a slide and I think about how I would solve this if A kept going, if A kept going for a long time, well, then it would be a lot of equations, right, if we'd only learned chapter 3. But because we've learned chapter 4, we can save so much time. And we can look at what chapter 4 allows us to do and to do a kind of a combo problem that involves chapter 3 and chapter 4. Questions about this? Yes. So this answer here, f at year 3, is what this is worth. And then converting, that wasn't what I wanted to do. F at p, remember I said that this is now I converted from F to P. That was that magic trick. That was exciting for you guys. And so it was P at 3 to F at 5. And so this value here, this $347, is what F at 3 is worth compared to what F at 5 is worth. That's the difference there. Any other questions? So you can use this to solve that real-world problem we were talking about the difference of saving for retirement if you started when you were 16 to saving to retirement if you started today and you retire at the same date. Because to do that, all you care about, let's talk about that. So if we're talking about the difference between you retiring today, starting your retirement savings today and starting your retirement savings a long time in the future, the difference is that you have these negative amounts for however many years until we get to today, and then you have a positive amount in retirement. Because the amount that would go here, this part is going to be the same either way. That doesn't change. So what we can do to solve that problem that we talked about is you can just calculate this using a uniform series from whenever you were 16 until now, and then you can transfer that money to the future using Chapter 3 and Chapter 4. Josh?
You could just subtract the totals too, right?
You absolutely could subtract the totals, but then you're doing more work.
Yeah.
You're calculating all of these extra lines that you don't need to do. Your calculator is going to be a lot more tired. The batteries won't last as long. I don't know. Okay. But you're doing more work by doing that. Questions about this? So this is a way that we can use Chapter 4 as a shortcut. Okay. So let's go on to example 4-7. So with 4-7, what amount at P needs to be deposited into a savings account that pays 15% interest to support 3 later withdrawals? These later withdrawals are this, this, and this. So you want to take out money, not at year 1, but years 2, 3, and 4. You want to take money out of the bank. How much money do you need to put in today? So this is really the cash flow diagram. And this one's tricky. Do you feel like you could use what we learned in Chapter 3 to do this? So to do this solving based on Chapter 3, let me show you what you do. We'd pretend that they're each individual payments. So P1 is going to be this value, P2 is going to be this value, and P3 will be this value. And the total of P is going to be P1 plus P2 plus P3. And if we only learn Chapter 3, this is exactly what we could do. We can convert these individual payments in the future to payments today. Do you guys feel comfortable with that? Questions about that? So that's Chapter 3, right? And when you do that, you end up having 3 equations, 1, 2, and 3. Because you're just converting, that's that one, that's that one, that's that one. That's why we have a 4 here, we have a 3 here, we have a 2 here. And so we get the answer. But it's labor intensive, right? You've got to plug it in 3 times. So there's another way to think about it. We could convert each of these to a future value. So we could convert this value to a future value. We could convert this value to a future value, this value to a future value, and we know, this one we already know the future value. And then, once we have all of these future values, F1 plus F2 plus F3, we could convert all of them back in time to P. That's another way to solve this. So if we're going to do it that way, well, that was frustrating. If we're going to do it that way, then what we can do is we can assume first that we're going to calculate f of 1, 2, and 3. Well, we know f of 3 is just going to be 2,000. That makes our lives easier. F2 is going to be this one. And F1 is going to be this one with 2 years, because we have 1 and then 2 years. And then once we have this f value, F1, 2, and 3, we can convert back to a p-value using what we learned in Chapter 3. And so if we do that, now we have F1, 2, and 3, and we convert back to a p-value. So that's another way to solve this problem. But we still are only using Chapter 3 right now. Right? There's nowhere that we're using Chapter 4 because we just have a series of individual payments. We're not doing any uniform series of any sort. So the next way to do it would be to have a uniform series. And we could have a uniform series where we're converting this instead of at P0, but at P1, because remember that if you look at the uniform series diagram, the first payment is 1 year after, 1 period after the start. Well, right here it's 2. So we could convert this to being a uniform series like this, right? So it gets converted. And then we can solve each of these for the future. Right? So we can solve for P at P1, for this one, for this one. And so what we're doing here is we're solving $2,000 for 3 years. And so, let me draw that again. Actually, let me just undo this again. So the way that we're solving this is we're saying, okay, look, we're going to convert from at P0 to P1, because that'll make doing a uniform series easier. And then, so now we have it at P1. And then we're going to convert this P1 to an A value of $2,000 and a single F value of $1,000. So here I have my $2,000 A value for 3 years. That's this diagram. Plus $1,000 2 years from now. And we're going to multiply all of this entire part, by find P given F in 1 year. So we're going to take this whole diagram here and then shift it back 1 year. That's what we did in this middle diagram. And that's what this multiplication does. It discounts it for 1 year. So it's a little bit more complicated, but if you have more than, say, just 3 payments, it makes your life way easier. And so that's the advantage of being able to use the uniform series. It saves you time in the long run. But it's important that you understand that you can use the uniform series equations as well as a single payment or single future value equation. So, questions about this? Yes, Matt.
You said about it going to the skips period to the 1 period?
Yeah, absolutely. So if we look at the uniform series payment equation, let's find P given A at I for N. Then what we have is we have a P value and we have an A value for however many years. This would be 0. This is 1, 2, 3, 4, and 5. So if instead I want to draw something where I have, this would be P, these would be A, I have P, and then I have nothing, and then I have A, then I have 0, 1, 2, 3, 4, 5, and 6. And so what's happening in that last diagram is that all of these A values were shifted over 1, like so. So they shifted over and they became this lower one. And because they got shifted over, then really that's the same as having this top one and then converting it back 1 year from P to P at minus 1, right? We could almost think about this as minus 1, and that's why. So one of the things that I think is important about this class that I want you guys to understand is that no matter what cash flow diagram you have, whether it looks like this, and then it's over here, another one. You can convert this, albeit painfully, and I want to know what is F. You can convert this, it'd be a pain, but you could convert it into one single F payment using Chapter 3. Because this would be one payment, this would be one payment, one payment, one payment, one payment. So each of these would be its own p-value. That looks like really annoying to solve, right? But you could do it. And so using Chapter 4, if you have a uniform series, and then I want to know what an F value is. Maybe I have some other value here. I can still do that, and I just solve for all of these together, and then I add just these individual ones. And then maybe even I convert all of this stuff to some number of years in the future where I have that F. But we can combine Chapter 3 and Chapter 4 to do anything related to the problems we've learned so far. So these are the 4 equations that we learned about for uniform series. Shall we move on beyond uniform series? I think so. I think it's a good idea. So let's do it. So if we want to figure out the difference between a uniform series or a single payment and at a present value or a future value, the way that it works is that we have find P given F is the inverse of find F given P. That's how these all work. The same is true for find A given P or find P given A. That's a neat trick when you only remember one of the equations, or if you're using your cheat sheet, but you got really mad at it and you scribbled something out, now you only have one of the equations, this is useful. It will also be useful when we get to the end of this lecture and we're learning a little bit how to do this stuff in spreadsheets. If we talk about compound interest, as we talk about this compounding interest like we've learned about previously, if we want to look at continuously compounding interest, you're basically taking the sum as the time continues to increase. But I want to move on. I want to move on to something more uplifting. Okay, that really doesn't make any sense yet because you don't know what arithmetic gradients are, but let's pretend that that was super funny. I want to move on to something more uplifting. All right, thanks. Arithmetic gradients are the next concept that we're going to learn, and they're when you have a constantly increasing amount of money. So maybe like if you get a regular raise every year or a bonus on top of a certain amount of money, that your increasing amount, this G unit, yeah, I love that joke too, increases every period. And arithmetic gradients are a more complicated form of a uniform series. They're uniform because we can describe them mathematically, but they're not just a horizontal line, they increase also. So, good question. So Saud's question was, do they increase by the same amount, the same factor? And they absolutely do. They increase by the G unit. So first year would be 0 times G, 0, OG, yep. And then you've got G, 2G, 3G, 4G, and then you've got like LTE over here. Okay, but you get the point, right? All right, fine, finally. But an arithmetic gradient is a more complicated cash flow that we haven't had yet. You could solve these using only chapter 3. But again, if it's a really long gradient, it's going to be super annoying. And the world hasn't ended at chapter 3, so we learned chapter 4, so we get to do this more easily. So, salary might be this way. Maintenance costs, if you think about increasing maintenance costs as a car gets older, for example, might be this way. And what we want to think about is we want to think about this G, exactly to Saud's point, that's going to be a fixed amount of increase or decrease each period. So at period 1, you have 0 times G, and then you have G, which is also the same as 1G, 2G, etc. And that's the multiplier by G. So it grows uniformly throughout. And here is the equation for finding P given G. So when we're trying to find P given G, we can use this equation. But we can also convert from a G unit, from a gradient, an arithmetic gradient, to an A value. So where would this be useful? If I want to figure out how much I should charge in annual maintenance for a car, for example, or for an HVAC system, or something else, and I know that the amount of cost that I'm going to have as the maintainer is going to go up, I can factor that in and convert it to a continuously the same cost. So the first year I'm going to make more money than it cost me. In the future I'll make less money, but it'll even out, and I can charge the person the same amount every year. Or if I want to charge up front for a maintenance package, and I know what the increase is going to be each year, I can also include this p-value. I can calculate for a p-value. And so if you're buying a warranty up front, that's really what you're doing. If you're buying that bumper-to-bumper warranty, that's what's happening. They know that it's going to increase a certain amount each year, their costs, and they're charging you all of that today. And in fact, they're charging you at some interest rate for their expectation of future cost. It might not be high, it might be low, who knows? But they're taking into account that they're going to get dollars, and they're going to spend dollars in the future to get dollars today. That's what's happening. So, let's do an example. Good old 4.9. Ah, yes. So, we have a certain cash flow. And if we take a look at this cash flow, we should be able to figure out that we actually have a couple of things going on here. The first part is that we have a series of costs. So let's look at what this looks like. We've got a series of costs that repeat every year, and that would be this value right here. And we know that because at this time, we have 0 at period 1. So we know what our value is for A. And then we know what our G value is. What's our G unit? G equals, who says it equals 5? Okay, I don't think so. Who says 30? Yeah, it's 30. And we can see that because it increases from 0 to 30, and then it doubles to 60. So instead of being like 50 cents, the G unit is 30. Never mind. But you get the point, right? So G would be 30 here, and if you see the difference between each of these, it's going to be $30 more. So if we want to calculate how much this is going to be worth in today's dollars, in P, right, what's the P value? Then I have this $120 uniform series, that's this right here, for 5 years, and I have this $30 arithmetic gradient for 5 years. And there's a trick to this that many people make a mistake on that I want to point out because you guys aren't going to make that mistake. I'm pretty confident in that. And the mistake is that people forget that at time 1, an arithmetic gradient has a value of 0. And so the number of periods is going to be the same as that uniform series. And sometimes what people forget is that even though there's this 0 value for the first year here, they think, oh, well, I only see 1, 2, 3, 4 values for G, so I'm going to change this number to 4. But that is not what we're going to do. You guys are smarter than that because you came to class on a Thursday. Got it? So, bless you. So a certain piece of machinery is expected that the expenses are going to be as follows for a piece of machinery. And we want to figure out if we're going to calculate a uniform annual maintenance cost, how much that should be. So why don't you guys take a minute and try to solve this on your own. So we've got our costs here, and there's a few different ways that we could solve it. I would encourage you to try to solve it using that new concept that we just learned, arithmetic gradients. They're super cool. And you can use your cheat sheet to take a look to figure out what the arithmetic gradient equation would be. So why don't you guys take a minute, work on your own. If you get stuck, then you can ask a neighbor.
I think so, because you can't. Yeah, there's nothing on there.
We should suggest that for the cheat sheet. The question is, what is the uniform maintenance cost over 4 years? So if I want to charge somebody the same amount every year and cover these expenses, oh yeah, I should have probably told you an interest rate. That would be helpful. So at I equals 6%, and I want to know what a uniform series is, equivalent. What would that be? So it would be what the A, right? Because it's a uniform series. Yeah.
Would you mind explaining what exactly you did again in the previous problem?
In the previous problem, what we were doing was we were looking at how much of a p-value we'd have, an upfront cost,
So,
given an A and a G. And so we know how to do the A bit, because we learned that last few classes. And then we just learned the G part just now. And so we used both of those two equations.
but why did you split it into two?
Because if you see that the G value, the G diagram,
This?
yep, the G diagram, the one right below it, the bottom one,
This one.
only, it does not include an A value, it only includes the G value. And so because it had an A value and a G value, you needed to combine both of them.
So we combine.
So to do the last problem, you needed to know how to do the very last diagram there, as well as the third from the bottom, that one. Because you need,
Series present.
exactly, because you need to convert that series, that underlying series, to present. And then you needed to convert, on top of that series, there was a arithmetic gradient. So you need to convert both of them back to present. Does that make sense? Did you have a job interview? Good.
Kind of the way.
Okay.
Turns in after class.
Yeah. Do you have a question? Okay. How are you feeling?
Better.
Good.
This time n is 5 years because of this thing we were just talking about, or is it still 4 years?
Why don't you take a look at the diagram in the book? And why don't you draw out the numbers of each of the periods?
1, 2, 3, 4, 5.
So, may I take a look at it? May I see your book?
Yeah.
One of the ways that I think about this is that if I was going to do this, I would write 0, 1, 2, right.
Except
And so, well, that wouldn't be 5 but you get the point. And so the same is going to be true if we think back to an A value here. The A value is happening at 1, not at 0.
Yeah.
So you actually have 0
0.
also.
Yeah, that's the point. Okay.
Yeah. That's a super important thing. In fact, that's something that I would talk to the people who are doing the cheat sheet about because I think it's going to be really useful. Did you have a question?
I was going to ask how you got it.
Okay.
Sorry.
Anything good? No? What's the uniform series for this problem? Cheat sheet? Come on, man. You should text as much as you want in class after you've solved the problem.
Yeah.
Then you should totally snap book and text chat, okay? May I?
Okay.
Well, I mean, do it if you want, right? But I don't know. Is it? What did you get for an answer?
Well, are we using this?
We're trying to convert to a uniform series,
Right.
but we also have a uniform series. Don't forget that part. So you should. Are these your notes from today's class so far? Yeah. Do you have any other notes?
I haven't.
Okay. Do you think that might be a problem?
Yeah.
Do you feel like you can solve the problem that we're working on right now?
Yeah, I think you use this equation.
Okay. So if you're totally following along and you feel like you're going to keep up, that's great. Absolutely do that.
Okay.
But if you're not, you're doing yourself a great disservice. Okay?
Okay.
Okay.
What is this $142 again? This is like the extra amount.
I love it. You guys are all wrong.
Are we?
You are.
Hang on. So to find A, right, given G is 100 here, right? Mm-hmm. Oh, G's not 100.
It's not?
It's not. Yeah, because then that would be 400.
Did anybody here get roughly $142? Oh, man. That's great. That's fantastic. Because, let me double check before I say this. Yes. $142 is totally wrong. Did anybody get a different number? Yes, all the way in the back. 494. Also not correct. Alvin? Nope. 841 also not correct. James? 488. Nope. Zero. Okay. So you guys are solving part of the problem correctly. And in fact, I noticed more than one person texting, playing video games, or doing something else fun, either before or after they thought they solved the problem correctly. So, you've all solved it incorrectly. Unless you got a completely different number than what I've heard so far. Yes?
Is it because we all use wrong formula?
Oh, you used partially the right formula. In part, you used the right formula. If we go back to this problem and we want to figure out what the present worth is, what do we need to do? I heard at least somebody go, oh, maybe that means that they figured something out. What might be missing from your calculation? Adding year 0 could be useful, but that's not what I was thinking about. Saud? Two parts to some degree. What else? All right. Then, so, to do this problem, we need to know a few things, right? First, for example, we need to know n. What does n equal to? 4, absolutely. We need to know I, 6%. We need to know g. What's g? 100. So if g is 100, then what's happening here at year 1? Isn't that when you have 100, but you have 0 times g, right? So what does that mean? Yes? A is 100. You also have an A value of 100. And so what does that mean? You forgot to add the uniform series that's happening here too, because what's happening is you have time 0, time 1, 2, 3, and 4. And you have a uniform series of $100 this whole time. But then on top of it, you have $100, $200, and $300, with this being your arithmetic gradient and this being a uniform series that you already have. So to calculate what the uniform series of this is going to be, a total is going to be A, which we know, it's $100, plus it's going to be $100, find A given G for 6%, n equals 4. And so, everybody that got $142, you did a great job at this. Right? That one is absolutely $142. And how much cents? 7 cents. Right? So you got $142, but what's the actual annual cost? A total. What does that actually equal to? $242.70 something cents. Because you forgot this underlying time 0. And somebody asked me about this when we were doing this. I think it was Aziz. It was asking, so how does this relate to the last problem? If we go back, we still have this A value of $120 that we're calculating right here. That's what that is. And then we add to it this arithmetic gradient. That's a key concept. So to solve this problem, you need to include the A value. Yes, Saud. You mean these numbers down here? This? The 4.32 is what the multiplier would be if you solve this P of A 5% for 5 years. If you solve P of A 5% for 5 years, then it's going to equal 4.329. So because in this problem we already know what A is 100, and we're trying to keep it as a uniform series, we know that this $100 A value here is not going to change. It's going to be $100 every year. So if I want to find out what the uniform series of $100 is every year, it's going to be $100 every year. So I don't need to do any modification to the A value. Somebody else want to try explaining that? How do somebody else think about this? Yes. Yeah, you could think about it as an initial value of 100, and underlying all of these is $100 because you have a G of 100, a G of 200, and a G of 300 here. If we have A is 100, and then G, it's going to be 0, 1, 2, 3 each year. I realized I forgot something in my excitement about this problem. It's time for stretches. So, you guys know how they go? Hands together, shoulders up and back, and then head all the way up. And head all the way down. Arms all the way out in front of you. And switch. Good. 1 foot forward, shoulders, and then your head. And switch, shoulders, and then your head. All right. So, we've looked at how you can convert from a uniform series with an arithmetic gradient to a present value, or a uniform series with an arithmetic gradient to a uniform series equivalent. If I ask you to convert from a uniform series to a uniform series, if I ask you, I want to spend $100 a year, how much money should I save every year to spend $100 every year? You're going to say, well, just $100, right? If I have an annual expense and I want to know how much should I pay for that every year, you're going to say, well, just pay for that expense every year. But if I want to convert an expense that isn't the same every year, that increases or decreases to an every year expense, then I need to use an arithmetic gradient. Aziz, you had a question. So A is not just the first deposit, it's this underlying deposit for the whole period. If you look at your diagram that you have on the cheat sheet of the arithmetic gradient, you'll see that at year 1, you have $0. And the differences between that and what you have in this example is that you have an underlying uniform series also. So in essence, what this problem is asking you is you have $100 each year. How much is that worth each year? Well, we know that that's $100. This A value is $100. And then you also have this arithmetic gradient going up on top of that, where you have G equals $100. And so what you need to do is solve both of these two problems. So if we go back to one problem previous, yeah, that's exactly right. If we think about it as we have $120 every year, all right, this is $120, I think you said. And then we have $30, $60, $90, etc. And that's the G value. And technically we have 0 times $30 in that first year. Just like technically we have 0 times $30 also. You got it. So to solve for P for this problem, you need to find P equals P of A plus P of G. And for this problem, A equals A of A, so just A, plus A of G. Yes? This, I would use this one right here. This one. To solve for P, if I wanted to solve for P, you're talking about with this example? Yeah, so I would be using in this, no, I would just use this, the A of A. Yeah, because that's what this is right here. It's find P given A. You could convert to a uniform series and then convert back to P, but that's just extra work. Yeah. Yes?
Would you use this in order for you to figure out the inflation, I guess you would say, for
You,
the year?
you might not use this for inflation because this is going to be a set value. You might include this if something increases in cost the same amount every year. So if something is going to increase, say, $50 every year, that would be a way of thinking about this. Yeah. Another example where you might use an arithmetic gradient. If you get raises that are the same amount every year, not a percentage of your salary. So after every year that you're at this job, you get a 25-cent increase or a dollar increase or whatever per hour. That would be an arithmetic gradient because it's just adding one more amount. It's not adding a percentage of that increase. So it's not like you're getting a 5% raise. You're getting a fixed amount raised. Oh, solving a problem with it. Sure. So, actually, let's go through a different problem that I think is kind of neat. And it's a twist on this. And here is an arithmetic gradient also. In fact, it's an arithmetic gradient and a uniform series, just like we were looking at before. Except, can anybody figure out what G is? G is negative, right? G equals, and what's the difference between these two? 6,000. So it's going to be negative 6,000. That still works. That absolutely still works. It's still the exact same concept. And what we really have here is that we have the equivalent of a $24,000 uniform series and a negative $6,000 arithmetic gradient. You add those together, and that's what you get. You get something that looks like this. And so, if you're thinking about this, and you're trying to figure out what you might have as a total cost or as a total income, and I want to figure out what my A value would be given, well, we know that A of A is going to be $24,000, right? Because it's written right here, it's just A. But we don't know what our A of G is going to be. But we just learned the equation for A of G, and that's the arithmetic gradient uniform series equation. And so we know that A of A is $24,000, and A of G is going to be $6,000 at 10% for 4 years. That's what we were given, I equals 10%. And so A of A plus A of G is going to be $15,714. So with these concepts combined, you can have pretty complicated cash flows. Instead of just having a uniform series, you can have a uniform series with an increasing or decreasing gradient, arithmetic gradient. You could also think about a uniform series with some other random payments using what we learned in chapter 3. You could combine and mix all of these together to come up with whatever kind of equation you wanted, overall equation that you wanted. But I don't want you guys to leave this class thinking this is the only kind of series that there can be. In fact, you might have already realized this if you looked to the other column of your cheat sheet. And that is that there's also something called geometric gradients. And geometric gradients, unlike arithmetic gradients, geometric gradients increase not with the exact same amount, dollar sum every year, but they increase by a certain percentage or decrease by a certain percentage each period. So you have an A value at time 1, and every other time after that, you increase by multiplying it by some interest, some increasing percentage. So with arithmetic gradients, if you get a 25-cent raise every year on your salary or on your hourly wage, that's going to be an arithmetic gradient. It goes up by 25 cents every year. So if you're making $50, you're going to make $50.25 per hour. If you're making $10, you're going to make $10.25 per hour the next year. But a geometric gradient increases by percent. So instead of getting a 25-cent raise every year, you might get a 1% raise or a 5% raise each year. Maybe 1% is more realistic. But you're going to be getting a percent raise instead of a dollar amount raise each year, for example. And that's what geometric gradients deal with. And so here are the two equations that you need to know for geometric gradients. The first one is when we don't know exactly, we know that G is not the same as the interest rate. So if G equals, say, getting a 1% raise each year or a 1% increase in cost each year, but we're using an interest rate of, say, 6%, then you're going to use this first equation. If the interest rate and the growth rate of G are exactly the same, then you can use this simpler formula. And there's one other thing that I want you guys to notice, that when we have arithmetic gradients, that we have big G. And you can think about it, it comes earlier in the alphabet. Arithmetic gradients are the original G. And then you've got geometric gradients, and they're a little g. They're like a junior G. And that's why we have arithmetic gradients and geometric gradients. We can tell the difference just by which G we're using. So if you're the chief of the G unit, arithmetic gradient. Otherwise, you're just a little g, geometric gradient. Maybe it's not as funny, but you get the point. And so one thing to note is that when you're using geometric gradients, you can only convert to p. You can still use a p-value to then convert to an a-value, but you only have the equation on your cheat sheet to convert to a p-value. So let's go quickly through this example. Using 8% interest rate, calculate the present worth, that means the cost or benefit today of maintenance cost for the first 5 years, where the first year's cost is estimated to be $100, and it increases at a constant rate of 10% per year. So what we're looking at here is we're looking at, I have times 0, and then I have 5 years. So 1, 2, 3, 4, 5. And here I have $100 But then that $100 grows at 10%. So I have $110, then I have $121, and so it grows. My drawing skills need some help. And so the G equals 10%. And A equals $100. And I want to know what P equals. I know that I equals 8%. And so to solve this, we can go back a slide to look at the equations that we just learned. And I is not equal to G in this problem that I just went over. I is not equal to G. So we have to use this big, annoying, complicated formula, unfortunately. And that big, annoying, complicated formula is already on your cheat sheet. And so what we know how to do based on that is we can solve and we can figure out what the present worth of that maintenance is going to be. How much do I need to pay today to estimate that I'm going to have enough money each year for the next 5 years for making these payments? Questions? So geometric gradients are exactly the same as arithmetic gradients, except that instead of having a big G that increases a dollar amount, they have a little g that increases a percentage. That's difference number one. Difference number two is that instead of being able to calculate a p-value or an a-value, with geometric gradients you can only calculate a p-value. Those are the two major differences between arithmetic and geometric gradients and the way to treat them. So we have our 10% here for our G value, 10%, and we have our interest rate here and here. We have our N's here and here. If this was increasing at the exact same percentage as the interest rate, the equation would be much easier, right? If we look back at our cheat sheet, we see that when I equals G, that the equation is P equals A1 N 1 plus I to the minus 1. And that's it. It's a much easier equation than this giant monster of an equation. But fundamentally, that's how you solve either of these. So what questions do you have? Yes, Aziz.
Can you also think of this as if we have 8, which is 100, and it would be pretty much a uniform plus arithmetic?
So if you think about this as a uniform plus an arithmetic, then so it's not, this is a good question. So Aziz asked, can I think about this as an arithmetic gradient plus a plus a uniform series? And you can and you can't. Conceptually, kind of similar. Actually not similar, because it's not $10 a year that it increases. This year it's $110 here. But this year, instead of being $120, it's 10% higher than $110. So it's going to be more like $122. And then this year, it's going to be 10% higher than that, and 10% higher than that. And so every year, instead of just increasing a fixed amount, you increase by a percentage over the previous year. That's the chief difference. If it wasn't a constant rate, you'd wait for another lecture when we're going to talk about that. Good question. If you knew how many years it was and you knew the amount every year, you could use chapter 3. We know chapter 3 already. You could just solve each year as if it was a certain future value, convert to a present, and then you could convert using chapter 4 to an A value if you wanted, or you could leave it as a present value. If you have an example of retiring in 65 years, it's really annoying because you don't want to do find P given F or find F given P 65 times. That would be annoying, and that's why you're going to wait for the next lecture. Before we go on to the next lecture, because it's still today's lecture, we're going to talk briefly about continuous compounding. And continuous compounding, we remember from chapter 3, it's when the interest rate increases continuously, so the compounding interest accrues continuously opposed to every quarter, every year, et cetera. And the main difference is that we have slightly different equations. And the slightly different equations just substitute in our E values, just like we were using previously, to find A given P, or find A given F, or to find F given A, or P given A. So here are all four. And these are only relevant for finding A, F, or P when you have a continuously compounding interest rate. Every other time that you don't have a continuously compounding interest rate, you're going to have an annual interest rate or an interest rate per period. You're going to use that instead. Only on problems. So I don't think we need to really spend much time on this because the only difference is that you only use these equations, you use them the exact same way. You only use them when you have a continuously compounding interest rate. And you'll see them on your cheat sheet right over here. So there's an example 418 that we could go over, but I'll post to Canvas a little bit of discussion about 418. And we can solve the same way. So, Aziz asked, what if I have a really complicated cash flow setup? And I said, wait for another lecture, Aziz. I didn't say it like that. What I was hinting at was being able to use spreadsheets. Because before they had Microsoft Excel and the other kinds of Lotus spreadsheets and things, people got really sick and tired of doing all of these equations by hand. So when they had computers that were capable of it, they programmed how to do the equations that we've learned so far already into spreadsheet programs. And so let's take a look at a quick example. If I know that I have these cash flows, so A equals $100, and I want to calculate what the present worth would be or what the future worth would be with an interest rate of 7%, we can do that. We learned chapter 4. We know how to do that. So far in chapter 4, this is just a uniform series. Find P given A or find F given A. We could do that. But if we have a complicated cash flow where you have $100, 60, 600, 47, 1, 12, 53, it'd be really annoying, like we were pointing out earlier, to figure out, because we'd have to solve find P given an F of $3, given an F of $50, 12, 1, every single year. That would be a big pain. But using spreadsheets, we can do it much more easily. And so let me show you briefly how to do that. So we can construct these cash flow diagrams in a spreadsheet by entering each line of our cash flow, each period, et cetera. And we can have a setup for uniform series. So we have a net present value equation, and we have find a future value equation. An important part of this is that the future value equation is set up automatically for uniform series. And so I'm going to go over two quick examples of how to do this. So given that a spreadsheet where we have a cash flow of 0, 100, 75, and 12, this would be a real pain in the butt to do if we were having to do find P given F, find P given F, find P given F. But using the NPV Excel sheet equation, you can also use this in Google Sheets or some other open office spreadsheet program, same equations. You can include what is the interest rate, which is B7 here, and then what are the cash flows? And the cash flows are, oh, I made a mistake here. Yep, their cash flows are for period 1, 2, and 3. So the cash flows are B3, B4, and B5. B3 to B5. And that automatically calculates for us what's that net present worth, as if it was doing a bunch of find P given F, find P given F for every single line. And like I said back a couple of slides, that if I want to find the future value of something, then what I want to do is I know I know N, A here is 0. And here's why it's 0, is because we have no uniform series here. Instead, we have a p-value, which we just calculated. And so we have B7 being the interest rate, 3 being the number of periods. We have no uniform series, and then we can use B8, which is this value here, B8, which is the same as P, to calculate what our future value is. So it's one extra little step to be able to calculate what a future value is. But this is basically find F given whatever cash flow diagram you draw into this system. That's a really powerful tool, and it's really nice. You guys will probably want to use this, say, in your 195 class, later in your career when you're figuring out cash flows. We'll probably talk about it more this semester. And there's a few other kinds of equations that I'll post up on Canvas as examples, but we don't need to go over. So, thanks for your attention today. Have a great weekend.